Guten Morgen. That is the tiny bit of very bad German we are going to speak today.
But you're actually Dutch, right?
I am Dutch, but
so you're
German is terrible.
a one-off of German, right?
Yeah, just one off.
Or
We're the small neighbor, right? So yeah, I'm Martijn, this is Kirk. We have a small performance tooling company called J-Clarity, but the reason why we are here today is to send you a warning. And the warning is that this guy is coming for you. Have you seen the Terminator movies, Kirk?
Never.
Never?
Never seen one Terminator movie.
Not one.
So I'm just completely ignorant about what's coming after me, right? So I'm very curious to hear what you're going to say about all this.
Okay, excellent. Yeah. So for those of you who have seen the Terminator movies, you'll know that humans don't do very well against the machine, which means you guys. And this is what we're facing today. You recognize this, Kirk?
Yep. I think I just bought one of those.
Awesome. How many euros?
I hope I didn't buy the other one. So, how many euros? Yeah, it was. Well, I'm not sure. I'm not sure. It was rather expensive, but a very small piece of hardware that made a huge difference. Yeah.
So this is a
it's an i7.
It's an i7.
Yeah, it's pretty much just a high-scale photograph of what the layout looks like.
But
yeah.
We'll go back in time, shall we?
I have no idea what we got here.
Let's go back in time.
Hey, Marty, do you know what this is? Does anybody know what this is?
There must be at least one hardware geek in the room.
Come on. Can't be all just software geeks here, right?
Nobody recognizes this. I will buy you a beer. In fact, no, Sebastian will buy you a bottle of scotch. I can say that now. Yeah. If someone can tell me what this piece of hardware is.
Hey, there we go.
Well, there's always one in the audience.
There's always one in the audience that knows what this is, right?
See Sebastian after the talk.
This is the absolute first integrated circuit that, well, CPU that was produced by Intel. In, when was that, 1971?
I wasn't even born then.
You weren't even born then,
wasn't
right?
even born
so
then.
This even predates you. So what does it actually look like? Ah, there we go. See that nice little piece of, so, you know, I got this nice i7, and well, actually, I've never used one of these either. But you know, we used the predecessor was the, you know, multiply by 2.
Okay, well let's see how much power one of these 4004 Intels gives you.
Look at that, 2,300 transistors. Can you believe that? Right, 16. The instructions, all of the instructions, you can read them like in a single, really, really thin document. And, well, they're only, well, 12-bit addressing, 8-bit instructions, 4-bit words. Wow.
That's an interesting history lesson as well. Who here is, yeah, those were days. Who here has done 16-bit computing? Coded 16-bit. Anybody 8-bit computing? Yeah, see, you coded on one of these guys.
I've actually coded 1-bit computing. It's really, really fun. You just have to have a lot of processors. In this case, we had 32,000 of them. So,
Kirk won't tell you how old he is, but he just gave it away.
1-bit computing. It was really fun.
1-bit computing.
Yeah, and look where we've gotten to, right? Now we're into this monster beast here. What do we got? Like 1,370 landings. For those of you who don't know what that means pins, places where you can actually make contact with the chip. And the problem with the current chipsets is that we've got no more room to put any more of these on. We're like completely full, right? And the documentation that comes with this chip, well, we sent one of our developers off to read it. Has he ever come back?
He's on page 4098, apparently.
Right, and so okay, so he's about 1/10 of the way through. Yeah. Yeah, so I mean, even the documentation on the diagnostic section of the chip is infinitely more complex than the original chip.
Horribly large.
And this is the type of thing that we have to deal with, right?
Yeah.
And it's only getting worse.
It is getting much worse.
Much worse. Yeah.
So we have lots of challenges. We have issues with hardware threads or threads in the operating system.
Or number of cores.
For the
non-hardware types.
we have this challenge of virtualization. Who thinks virtualization is going to save us?
Nobody.
Good. We have a smart crowd today.
Honest, yeah, okay.
And last of all, we have the JVM itself having a major challenge. The JVM and Java need to evolve to meet this new world of the new complicated machine.
And if we had more time, we could even talk about the language challenge, which is even
trickier. Shall we say.
Absolutely.
But first of all, I think we're going to go back to some basics. Does everybody remember their statistics and graphs from university?
Yeah, probably.
Has everybody had their coffee? Because it's not going to get much easier, I can tell you that right now. So we're going to cover a few small laws that I'm sure everybody is very familiar with. If you're not, then hopefully by the end of this talk, you will be. So, the first one.
Moore's Law?
Moore's Law.
It's not about clock speed, it's about transistors. In that huge complex picture of the i7 we saw, we have a chip, right, that has so much wiring, well, effectively wiring in it, that you can't get a clock cycle from one side of the chip to the other in the duration of a clock cycle, right? So you can't get the pulse across, right? Which means now we have to be selective in the paths that we choose in order to get the clocks into the right places. So what does that mean? It means things like we have this nice activity going on known as CLM, which is core level multi-threading. So we've always considered that, you know, thread scheduling happened at the level of the operating system. Well, not anymore. It actually happens inside the hardware itself at the level of the chip. So we ended up with the situation where we just have so much going on inside the chips that we actually just can't get clocks through them anymore, which makes for some interesting conditions. But more to this particular graph here, right? What it's saying is that even though we have all these complexity problems, you know, with clocks and stuff like that, which have effectively said we can't go any faster with the clock, we're still adding transistors to the chips in the same amount of real estate at the same rate as ever. It's still just going, you know.
Yep. And so we're having to go multi-core. And it started with 2, and then 4-core machines started coming out, then 8. Then people like Azul Systems started putting out machines that had 7,496 cores.
7,000? Did they get to that many?
Yeah, they got to that many.
That's amazing.
Even in your mobile device now, many of you have a dual-core mobile chip in your smartphone.
And you'll have quad-core pretty certainly. What did Gosling say? He said everybody would have 1,024 cores on their
mobile device.
On their device by 20-something or other, 2021 or 22.
So that's
he's
easy.
wrong, actually. But we'll get to that later.
We'll get to that. Next law, Little's law. And this is all to do with serialization. Now, we're going to try and speak in terms that hopefully people from Munich understand very well. So you have a beer hall in Munich, which for me is very important because I come from London, and beer is very important to us.
Well, they actually have that one downtown that has like the huge barrel.
Right.
I don't even know how they get that barrel in and out. It's it's quite amazing. And you know, they have the guy there. It's just they just open the tap, so the beer is continuously pouring out, and they just have these 1-liter mugs that are just sort of like going through, like this.
Right. Exactly.
Right? You know, so really, the rate at which they can serve the beer is determined by the rate at which the beer flows out of the tap.
Right. And so there's always this point of serialization, which is how fast the beer flows, which unfortunately we can't make any faster.
Well, you could by having a bigger tap. But
you could have a bigger tap.
Really fun. But anyways, that's exactly what this formula is here, right? So if you look at mu as being the rate at which the beer pours out, right? We can say that the number of beers we pour is dictated by this particular formula here. Actually, we don't have a beer icon for that.
We need to have a beer icon for that.
Yeah,
it's terrible.
Absolutely. Right? So throughput equals 1 over service time. And this is a real fundamental law that affects all kinds of things that we do, and it certainly affects you know, how well our applications can perform inside these
multi-core machines.
Multi-core machines, even single-core machines. If you think about it, right, if we looked at pre-2005, We all basically coded by the Quake principle. That's how we tuned. Has anyone heard of the Quake principle? Right? What you do is you ask your customer, like, okay, or they come to you and they say, okay, well, we need this application to run faster. Well, how much faster? About twice as fast. You say, no problem. Project will take 18 months. So you go back to your office, you play Quake for 15 months, you come out, you say, order this hardware, and boom, everything runs twice as fast. Right? Because with the clocks going twice as fast, mu got slower, smaller and smaller, smaller. So that means, the amount of time to execute the same number of instructions effectively with some, caveats. Yep. Got smaller, which meant that throughput just kept going up and up and up. But, unfortunately, the burden of making the programs go faster has fallen away from the hardware guys and is now onto your shoulders.
Yep, certainly back on us, which means...
So not really a news story, but
yeah.
Still fun.
And so no more playing Quake for you guys. You actually have to do some real work again.
Yeah. Well, do they play Quake now, or is there like that war thing?
Call of Duty Modern War. I don't know.
I don't know. Warlock,
whatever the kids today are playing.
Okay, whatever.
Next important law.
Amdahl's law.
Amdahl's law. And this is the one where we talk about parallelization. So basically what we're saying here is how much of your overall system or overall application can you actually run in parallel and get performance and speed benefits from that. You're always going to hit a point of serialization. Okay? The beer can only flow so fast from the tap in the beer hall. However, if you have more and more servers behind the bar, it means you can have more queues of people lining up to get their beer, which means for the overall throughput of the system, you have more people, more happy people, with a good, nice German beer in their hands.
Do you really? I mean, that all depends on the number of taps you have, doesn't it?
It
and the
does
number of
depend on the
servers,
number
right?
of taps. That's right.
So if you only have one tap, then you're going to just, instead of having all the people, well, you're going to have all the people lined up, and then you're going to have all the servers lined up, still waiting for the beer. But if we had more taps...
Then would be more parallel.
If we have more than one server.
Yes.
So you sort of have to play these types of games with things, right? And that's effectively what this formula here is saying, right? If the rate of serialization in our application is 100%, right, then this whole formula collapses into a value of 1, and that's the number of cores your application can use, right? Think of the startup code in your system. It's generally always single-threaded. Think of your compiler. It's generally always single-threaded. XML parsers, things like that, right? They can only take advantage of one core. However, if you can fully and perfectly parallelize those things, then F goes to 0. And when F goes to 0, then this effectively collapses to N, which means I can use as many cores as I can throw at the problem.
Mm-hmm. And these laws might all seem a little bit abstract to you right now, but to give one small practical example, do we have anyone here who codes Scala? Yeah,
one.
Two Scala people.
Two Scala people. Wow, that's a lot. Okay.
Okay, so...
It's getting popular.
So this story is going to be a little bit difficult to tell then, but very briefly, so Scala has its own compiler. And for a very long time, the Scala compiler was a major, major performance bottleneck because it could not be parallelized. It could only work in a single thread. And it was actually not until Kirk and a few others talked to Martin Odersky and gave some advice on how to make the compiler more parallel that they then actually sat down with a piece of paper and used Amdahl's law to see how much faster they could make the Scala compiler. And today, with modern Scala, it's actually reasonably fast. So maybe there will now be more than 2 developers on Scala. Maybe tomorrow there will be 4.
Yeah, so we knocked 4 minutes off a 10-minute compile. Yeah. Over dinner. So
what are the popular languages here in Munich? Are people coding Haskell, Lisp? Is it all Java? All Java. All right, we got a dedicated Java.
Groovy.
Few groovy
okay,
people. All right,
yeah,
we got some hipsters in the crowd. Excellent.
Well, we'll give you a hint on this one, right? This still applies. You can't get around it.
You can't get around it.
Yeah.
as software developers, we are very, very good at taking away the advantages that hardware is giving us. Okay? There is nothing more amazing than a software developer's ability to take away the performance gains that hardware are giving. If anyone's used the latest version of Eclipse, you'll know exactly what I'm talking about. Or Microsoft Word. So the point really being is that hardware still has finite capacities. There is only so much hard disk, there is only so much RAM, your CPU is only so fast, it only has so many cores.
And the one that people often forget, which is really fun, is you can only get so much data in and out of the CPU to RAM, right? These are known as memory bandwidths. So there's all kinds of these hidden measures that no one even considers when they're writing their application that we've run up against just people exhausting the finite capacity of hardware with their application.
So unfortunately, in this modern world, with the hardware constantly changing, multi-core machines, being able to use things like graphics cards, GPUs, SSD drives as opposed to hard disks, all these physical changes is something that you now have to be aware of in order to make your Java code run efficiently. So we talk about mechanical sympathy, which is a phrase from a colleague of ours in London called Martin Thompson. Has anyone heard of the disruptor framework? A few people. So it is actually the fastest trading application in the world, and it's written in Java, not C or C++. And one of the reasons why it is so fast is because Martin and his team took a very careful look at how the JVM worked and how it mapped to the physical hardware underneath. It does take a lot of extra time and effort, but they've managed to get better performance than native code, which is very, very interesting.
Yeah, I would say that this mechanical sympathy idea goes back quite a ways because when we were actually programming on Cray computers, this is exactly what we did. We studied the CPU, we looked at our algorithms, we said, how can we best take this particular algorithm and change it so that it works in harmony with the hardware as opposed to working against the hardware. And what we find in a lot of Java applications is that that the application is working counter to how the hardware would like you to work, and you lose a lot of benefits of the hardware, just by making what I would call minor changes to your coding style, that would make a huge difference, and really without any sacrifice to readability, or surprisingly without sacrifice to readability, or some of the design principles that we hold near and dear to our profession.
So what can you do? We've given you these abstract laws, and it all seems a little bit theoretical and academic. So one of the things we suggest is to make sure you have these laws near and dear to your heart. Okay? Go to your local beer hall and see the laws in action. Okay? Participate in the queues. If you want to earn a little bit of extra euros, participate behind the bar. If you want to spend all of your euros, keep drinking beer.
Are you suggesting that they should all... Right, okay.
Yeah. But most crucially, understand the hardware that you are running on. Dust off the old hardware manuals, make sure you talk to your system administrators, and actually find out what your Java is really, really running on.
Right, so yeah, drinking beer will help you appreciate this talk. It's fantastic, I like it.
So hopefully we haven't lost you yet. We're now going to go into some assembly language, some lambda calculus, category theory, and monads.
I'm leaving.
We're only joking. So we're going to talk a little bit about cores and hardware threads and fork and thread and other such fun topics.
Why don't you put that point in? There's no such thing as a thread.
There is no such thing as a thread.
Threads are non-deterministic. So if there's no such thing as a thread, why are we talking about threads then?
To confuse the audience, Kirk.
Oh, okay, gotcha. Yeah. Okay, you've confused me too.
Okay, that's
What do you mean, no such thing as a thread?
So there's no such thing as a thread, right?
Okay.
If I'm a CPU, or if I'm a piece of hardware, I have no idea what a process is or what a thread is, and I don't care. Okay? All I'm doing is just processing a sequence of instructions that get fed into me. And I have absolutely no idea of the context that this is happening in.
Makes sense to me.
Yeah?
So as a CPU and I'm looking up at the world, I'm just seeing streams of instructions and data coming at me.
Yep.
And I don't really have a clue where they're coming from or who they're associated with or any nonsense like that.
I have no intelligence about it. I don't know how to optimize it very well or anything. That's up to the level above me.
Like local optimizations, and that's pretty much it.
Just like the Matrix, all that code flowing down.
So then why do we talk about threads then?
Well, let's define a thread first, shall we?
A thread is defined as a locus of control and an instruction sequence and abstraction entity which moves through the instructions of procedure as the procedure is executed by a processor.
Dear, oh dear.
Dear, oh dear.
Too long, do not read.
Yeah.
Right?
What is, okay. Okay, so what does that mean for the regular people?
Basically means it's a kind of an abstraction around a sequence or a flow of instructions, and that's about it, really.
That's about it. So it's just really a tool that we use to help us think about what's going on.
Exactly.
That sounds about right?
Yeah, so
okay,
something we invented.
Okay.
So threads are actually a giant leap from this kind of sea of instructions that the CPU see. So threads and forks were the first attempt at us trying to understand what it is we were trying to get to work in a sequence. You know, adding up some numbers, multiplying some numbers, doing all sorts of other things like that. I'll let you cover this one because, you know, this was back in your day.
Fork. Oh, I love fork.
I don't even remember fork.
Fork was really a simple thing, wasn't it?
It was. It was beautiful.
Right. So it was just a copy operation. We take the process, we make a copy of it, and we're done.
Yeah.
Absolutely no reason to communicate, so we didn't have to worry about shared state or anything like that. It was like a absolutely fantastic model, right? And, you know, but unfortunately people didn't like that, and they just wanted to you know, to have communication between threads and things like that. So
make it more complicated. They wanted to make it more complicated.
So yeah, more complicated.
Things were better in the old days.
Life was simpler. Ordering was guaranteed. I like that.
Happy days.
You don't have to think about it, right? Now we have this thing called new thread. It's like a lightweight fork, except for memory is now shared. And so we don't have to work hard to share state. As a matter of fact, sharing state happens all too easily. And that's a huge problem because sometimes often we share state when we actually don't want to. And, you know, there's a problem with the hardware in the sense that the hardware is actually, well, it has been in the past protecting us from some of the problems so that we actually couldn't see where this accidental sharing was occurring. And as we get more and more cores, what's happening is that we get more and more opportunities for this accidental sharing to show up in our code, right? So guaranteeing order is a much more difficult problem. We still have to start working with these things called volatile and synchronization.
Horrible
right?
things.
And you know what these things actually do is, you know, so since the processor doesn't really understand, you know, what's shared and what's not shared, we have to give it hints to say, hey, you need to do things, right? So what we do is we use these particular keywords, but what happens in the instruction stream is that we put this thing in called a fence. And a fence is really just an instruction that says, hey, you know, all that data that you're working with, you better throw it away and go back to main memory and get it, right? And we can talk about the consequences of that in a few seconds, right? So in a sense, what we have over time is this idea where hardware, operating system, and in the case of Java, the JVM guys are basically playing leapfrog with each other. So the hardware guys make some improvements. It puts some pressure on the operating system guys to actually make improvements in the operating system, right? And that's also put pressure on the JVM guys to make some improvements, but they'll make improvements that actually will come back now and put pressure on the hardware guys to make improvements. So, for instance, if we go back to the Spark V8 version, there was no such thing as a fence, which effectively means that there was absolutely impossible to have thread-safe code on a Spark V8. It was absolutely unsupported, right? So you can have a copy of one value hoisted into one register and the copy of that same value hoisted into another register, and there's no way of synchronizing them.
Okay, so that was the single core world. Now we're going to go into a little bit of hardware theory. Well, not so much theory.
So, well, yeah, it's practicalities, I would say, right?
Yeah. So if you remember the original diagram we had at the very start of the talk, this is Kirk's hand-drawn version of it.
Yeah.
Do you want to walk through it?
Yeah, okay. So basically we have cores at the top. In this case, we have 4 cores. And attached very close to the core is L1 cache. So, you know, what did we do with all these transistors that we put on the chip that we didn't know what to do with because, you know, we didn't quite know what to do with them? Well, we made memory out of them, right? So we got L1, L2 cache in this case. And we also have an L3 cache. So as you can see, the arrangement here is that L1 and L2 are private to a core. L3 is shared. And then eventually you'll be back by your main memory, and you'll have some sort of bus that will get you to main memory, and you'll have some sort of quick interchange path that will actually get you to the caches internally. So how all this works is that L1 cache, really cheap to access. L2 cache is the same cheapness to actually get to, but because it tends to be bigger, you have to walk through it to find things. And it's the walk time that actually makes L2 cache more expensive to deal with. And then we have L3 cache at the bottom, and that's even more expensive to get to. And of course, you know, by main memory, you're talking about essentially a trip to the moon in computing terms to get your data, right? That's all cool. So now what happens if I have a value in L1?
Well,
and I need to actually, go back 1 second here.
Yep, you're there.
Whoops, what happened? There we are. What happens if we have a value in L1 and for core 0, and we need, you know, core 1 needs that particular value, right? Well, we actually now have to develop this thing called a memory model. And the chips themselves have a memory model. And what the memory model says is, you know, how do these cores communicate when they have to share data values? And, you know, what are the rules of where things can be cached and where things can't be cached? And can I keep copies of things in different caches? Like, you know, some memory models will say, if I have it in the L1, I can't have it in the L2. And I cannot have it in the L3. Other memory models for other chipsets means that we'll say that, well, I can have it in both the L1 and the L2 if need be. But maybe I can't have it in the L3. So you can see there's all different combinations. And these different combinations of things actually sometimes accidentally protect our application from serious threading bugs or, you know, unintentionally shared data in this case. What's a cache line look like? Well, you know, basically these L1, L2 caches are not just individual memory cells. What they are these cache lines. And a cache line is 64 bytes of data. And, you know, how many cache lines do we have in a particular cache? Well, that depends on the size of the cache, obviously. But what it means is that our data is actually going to be laid out inside these cache lines. And, you know, okay, so let's say that we have a value X that we want to protect, and value Y that we don't want to protect, or that we should have protected, but we didn't. And they end up in cache line 1 beside each other, right? So what happens is that your program is going to run through, you know, for the protection for X, it's going to run through a fence. And that fence is going to cause that cache line to be drained. And when it's drained, it has to be refreshed from main memory. And, you know, so we'll get all the new values, you know, up into the cache, be reloaded into the cache, and life goes on. And then you go and make some changes to your application, and all of a sudden the changes in the application mean that X and Y no longer get aligned beside each other. As a matter of fact, maybe X gets into cache line 1 and Y gets into cache line 2. All of a sudden, the Y is not being flushed. And if we needed to protect that variable, all of a sudden we have a concurrency bug that was not visible in the first configuration, because the unit of concurrency from a core level is not a variable, it's a cache line.
All right, so we'll speed through this and give you some further context. So we've gone from this situation where we had everything happening on a single core. And now we've gone to a world where we have multi-core, so we can do things in parallel. But what we're looking at here is the problem of how do we share the data between those threads? Because the data could be sitting on one of those L1 caches. It could be sitting anywhere. So all of a sudden, it now gets a lot more difficult to share it and to make sure that we have a consistent value in that data. So this is a problem we face today. We can do more things in parallel, but we somehow have to protect our data. So this is something that Gil Tene said. We protect our code with things like the synchronized keyword, volatile, using Java util concurrent locks, these sorts of things. Here is a picture of a fence that was atomic until an earthquake hit.
Right. And yeah, that earthquake is that all of a sudden we have a cache misalignment issue where we had protection before. So getting back to Gil's statement, I think it's very important to understand, right? That means that we have to protect all the code that accesses a piece of data if we want to protect that data. And if we miss some part in our code, and this is what makes multi-threaded programming so fragile, if we miss even one point of access, then the whole thing breaks down.
Mm-hmm. Who here has had threading bugs in their code? Yeah. It's really hard to get right.
It's only 2, 3, not that many. Are their arms are broken, or they didn't understand the question, or they're right?
So we have this issue where, again, what Kirk was saying is that we have this visibility mismatch. Yeah. You have problems where the CPU does things in cache lines, and the Java memory model has a very different view of the world. So we'll just cover this quickly again. Where's Waldo? The variable x up there is a piece of data which is shared. Yeah, it has the volatile keyword around it to make sure that every time another thread wants to read it, it will come all the way back out to main memory, which is like traveling to the moon. Unfortunately, its little friend y here is also sitting in the same cache line, and it comes along for the ride. Okay? So all of a sudden, you think you've got this wonderful parallel code which is making everything faster. In reality, you're making the data travel to the moon and back every time, which slows everything down.
Yeah, because that's really like about at least 150 clock cycle stall for that particular processor whenever you do that. Yeah. And if you move forward a couple of instructions, and then you stall for 150, and then you move forward for 150 for a couple, and you stall for 150, when you do the maths, you're going to see that your utilization rate of your CPU is now less than 1%.
Okay. So,
and it doesn't show up in any profiling.
Nope. So we have to protect our code, and we have to protect our data. We have to make sure that when we're reading variable x from any thread, that we've actually got the correct value. Now, there's a whole bunch of different ways we can do this. We have the synchronized keyword, we can use atomic integers, it's all sorts of fun stuff. So let's see some of this in action. We're going to show some source code really quickly, because we're running a little bit behind time. But there is a point at the end of this. So here we go. If we're running naked, no protection of our data whatsoever, right? Our variable x could be in all the different cores being read and written to, and nobody knows. It'll be really fast, but you're not going to get an accurate answer. You could use volatile. This means that the variable x will be flushed out to main memory every single time, nice and safe.
No, that still corrupts.
That still corrupts. We can put fences around it using the synchronized keyword. So if you're a Java 1.4 style concurrency, this is typically what you'll use. We could use Java 5 style explicit locks. We can use the atomic integer, which uses a cas operation, which is a nice, fast piece of hardware-enabled operation, where you compare and swap values. However, there's a slight problem with performance. And this is a real graph that Kirk generated a couple of weeks ago using the latest Java 7 running a benchmark. And it is orders of magnitude slower to protect this data. So again, in this multi-core world, you might think that you can have all this lovely parallelism and run these parallel threads, but it means you have to protect your data. And if you protect your data using locks, it's going to be very, very slow.
And I equate sort of locks as programming by exception, right? Yeah. We use a lock just in case
something goes wrong.
Right, and it's a very pessimistic model. And if there's one thing we can learn from the database vendors is that pessimistic models don't work, which is why they've all tried to move to more optimistic locking models for data protection models. And then we need to do the same thing also.
Okay. So we've talked now a little bit about cores and the problem with sharing data. So the other thing we're going to talk about very quickly is virtualization, because this is another trend that is happening because, quite frankly, a lot of people are not understanding the hardware that it's running on. So why do we do it? One of the reasons is administration. Okay? System administrators, in theory, will find it easier to monitor lots and lots of virtual machines. But a lot of people do it because they think they're going to utilize their hardware better. Okay? People think that we are wasting hardware today.
But we are. We're wasting a lot of CPU.
Yep, wasting a lot of CPU. So people think that you should virtualize your hardware so you can utilize that CPU better. But as you just saw with the hardware threads example of the data having to move between cores and things, chances are it's actually just your application is not very well tuned to utilize that CPU.
And even if it was, the CPU is the fastest component of the computer, and it relies on other much slower components to feed it. Mm-hmm. So the problem really isn't that we're not getting good saturation on the CPU because of because we don't have enough to do. It's that we just can't feed the beast. And if we look at CPU speeds compared to memory speeds, we see that there's about an 8% gap per year in the speed improvement, and which means that this problem of the difference between the speed of the CPU and being able to feed it is just getting bigger and bigger on a year-in, year-out basis. So it's not that we should not go to disk anymore. It's almost like we should not go to RAM anymore.
Yeah. So the key thing is you cannot virtualize yourself into more hardware. So one aspect to look at is your application actually using the hardware correctly today? The other issue is don't over-virtualize your hardware. So we've run across several clients who do things like they have 16 gig of RAM on the hardware and they allocate 8 virtual machines of 8 gig of RAM each. 64 does not go into 16 very well. So one of the things we say about virtualization is that you need to actually plan for this properly. Look at your total cost of ownership with your bare metal, your hardware. Look at how your applications are running on that hardware. Make sure that it's not just badly running applications that are underutilizing your CPU. And only go to virtualization if you really, really have to. Now, there are a bunch of tricks you can use with virtualization to make sure that the virtual operating systems, as it were, are utilizing the hardware as best as it can. So you can pin a VM to a CPU core or to a bank of memory, which can help.
Yeah, this trick only works because of the newer structures of the processors. We no longer have these like front side, back side buses. What we have are fast path, slow path access to memory. And so the CPU and memory pinning tricks all rely on the fact that I'm going to get good processor to memory affinity, which means that I'm really limited to single-threaded applications. Mm-hmm. So really what we're doing is we're turning our quad-core or multi-core, 8-core machines into 8 single-core machines again. So it's like Back to the Future type thing.
So if your CIO or CTO comes back from New York with the little trade magazine in their hands, this is how dangerous virtualization can be. So tread lightly and tread with care.
Yeah, you might get the result you're expecting, but then again,
you might not.
Yeah.
So there are a lot of reasons to move into the cloud and to use virtualizations. But as Kirk has said in a rant about 2 years ago, performance is not necessarily one of them.
Yeah, there's many applications that are well suited to the cloud, and there's certainly a lot of benefits from capitalization points of view and from administration point of views. There are, under special conditions, you can get better performance in the cloud, but they're very limited conditions.
So we have one last challenge, the JVM itself. And most of you here are very familiar with the JVM and Java, so we will be able to go through this section nice and quickly. Does anyone remember write once, debug anywhere? It's the marketing statement from Sun. Yes, right.
That's all about the hardware.
So first of all, Brian Gertz and Mark Reinhold and the other folks in OpenJDK have a lot of work to do to get the JVM up to speed with modern hardware. So one of the problems with write once, run anywhere is this massive abstraction level problem.
Yeah, we're completely abstracted away from the operating system, which actually means that there's a lot of things that we can't specify. We can't specify a lot of behaviors of threads and other things. We try to mask them over with a Java memory model, but still the abstractions leak through, with the differences in the hardware.
Yeah. Do we have Android developers in the room? Android developers?
Yeah, quite a few, yeah.
How much fun is it to write Android apps for the 1,048 different configurations for the display screen?
Yeah, that's a real art, right?
I mean, you guys will be in a job for life. It's awesome. But again, Java is abstracted away from this. It's very difficult to actually do this easily.
And there's nothing to do with power there at all, right?
Yeah.
It costs a strong memory model. The JVM is ultra-conservative, so there's a lot of optimizations that could be applied. We're just not going to apply them because we can't guarantee correctness. And correctness must be guaranteed, right? So locks enforce correctness, so people are going to use locks because that's the, shall we say, brain-dead way of making sure that everything is right. And sometimes that's just the best way to do it, right?
Garbage collection, this is a fun one.
Yeah, I speak about garbage collection a little later this afternoon. But garbage collection is dominated by the number of live objects in the heap, right? And the larger and larger and larger the heap we have, the more live objects we're going to have. And there's actually other activities that actually have to traverse through heap, and they just take longer, right? So large heaps are just going to become a huge scalability issue with current garbage collection technologies.
So if you think you've got a GC problem, like an out of memory error or that sort of thing, and you go, I'll just throw 32 gig of heap at it, you're actually causing a different problem. It's going to take the GC a very, very long time to go through and find all the live objects.
Yeah, and so what people have been doing is they've been looking at using different techniques to get these stuff out of heap, away from the garbage collector. So they have these things which we call slab allocators. And slab allocators really hide the problem in one sense, so that's good. In the other sense, if you get too granular with your slab allocator, you're effectively writing your own garbage collector. And I can tell you that writing your own garbage collector, I can count on my hands how many people are actually able to do something like that.
Qualified to do that.
Yeah. It's a really hard thing to do, right?
So GPU is another interesting one.
Well, remember we said at the beginning that your machine has like 8 cores or 16 cores? We lied. The current MacBook Airs are shipping with more than 800 cores, right?
Yeah.
When you consider the GPU. If you look at Project Sumatra, which is on its way, that's going to give Java complete access to all 800 cores. And that's going to be within a year. So within a year, you're going to have access to a reduced instruction set processor, but like 800 of them, right? On top of the not so RISC style cores that you already have access to today. So we're going to get to that 1024 mark way, way sooner than we thought we were. The question is, how are we going to use them?
Yep. So in conclusion, we're warning you that you should learn about your hardware again. There's now a multi-core world. Memory has changed. Your hard disk has changed. Networking has changed. All these things have changed. So instead of just throwing more virtualization at it and thinking the problem will go away, Instead, take a look at your hardware capacities and ensure that your applications are utilizing that hardware correctly. Learn to use parallelism in your code. Amdahl's law, learn to have lots and lots of queues at the beer hall, because as Kirk just said, you've already got hundreds, if not thousands of cores coming on your machine tomorrow. And if your applications can't use those cores, then you're wasting a very expensive hardware.
Well, you're wasting opportunities to beat your competitors in the performance market.
Yeah. So don't become extinct. Don't go the way of the dodo. Be like Sarah instead. Fight the Terminator. Fight the machine. Learn about the machine. Some quick acknowledgements for people who gave us some helpful pictures and hints and bits and pieces. And thank you very much for listening.
Thank you.